All right, ladies and gentlemen, this is going to be sequences and patterns dealing with arithmetic and geometric sequences recursively. This is going to be part 2. Okay? So what we're going to do here is start looking at some actual patterns. Some like picture patterns. We've already discussed geometric sequences, arithmetic sequences in the previous lesson. We've talked about our formula for determining the R value or the D value, the common ratio or the common difference. We've talked about that. We've talked about how to find the first term, which is pretty obvious. It's the first term. And so now let's actually apply this to some interesting problems. Here we have the number of tiles that we're interested in. Your job now will be to analyze the sequence and then circle the appropriate type of sequence. Okay, so we want to get the type of sequence. Is it arithmetic? Is it geometric? If it's arithmetic, then we want to find the common difference. Or if it's geometric, then we want to find the common ratio. All right, then we're going to circle whether the sequence is finite or infinite. Okay, so the number of tiles. In this particular problem, I see 9 tiles. Then I see how many tiles? 12. And now we have how many tiles? 3 times 5 is 15. And 3 times 6? 18. Okay, so now check this. What do we do to go from 9 to 12? Okay, add 3 tiles. What about from 12 to 15? Add 3 tiles. 15 to 18? Add 3 tiles. So, there's this common theme, this common pattern of adding 3 tiles. Does that make this arithmetic or geometric? Definitely makes this an arithmetic sequence. It is not geometric. So if it's arithmetic, then what is the common difference? The common difference is 3. Okay, and now, does this pattern go on forever? Well, it could, but it stops here. There's no indication that it continues going, so we're going to say that it's a finite sequence. All right, so you can make those markings on your notes. Next up, here we have the number of toothpicks. Number of toothpicks. Okay, so let's count it. 1 toothpick, 2 toothpicks, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I count 12 toothpicks right here. In the next picture I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 on the bottom row. The second row is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 toothpicks. And so that's a total of how many toothpicks? 22 toothpicks. And over here we got 12 toothpicks. 12 and 22, that's great. Now what about over here? Well, I'm going to assume this is 12 toothpicks, this is 10 toothpicks. What do you think's next? 12, 10,
8.
Probably 8. Let's count it. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 toothpicks. So a total 12, 10, and 8 makes 30. There's 30 toothpicks. Okay, so my question to you is, how do we go from 12 toothpicks to 22 toothpicks? There's adding 10, yeah. Now, can I add 10 and get 30? No. Wait a second. So I add 10 here and then I add what, 8 here? Is this an arithmetic sequence? No. Absolutely not. You have to add the same difference or the same amount each time for it to be an arithmetic sequence. So, all right, our next question: is this a common ratio instead? Do we have a geometric sequence here? So, let me just kind of cross through that because that's useless to us. What do we multiply by? 12 times what is 22? 12 times what is 22?
You can't do it.
12 times what is 22? 12 times what is 22? Hopefully you're trying this on your calculator. 12 times what is 22? How'd you get 1.83? Okay, so now finally I get some action out of you guys. What you have to do is take the second number and divide it by the first number. So what is 22 divided by 12? 1.8 and then 3 repeats, right?
Yeah.
Okay, good. Now what is 30 divided by 22?
It's a 1.36.
1.36 and the 36 repeats, yes? Okay, now hang on a second. Look at this. You have 1.83 and you have 1.36 as being multipliers to get to the next term. Is this a geometric sequence?
No.
Absolutely not. You guys are doing great. So it's not arithmetic, it's not geometric. That makes it neither. And therefore, we're done with this problem other than, is this a infinite or finite sequence? It's finite. Okay? Let's keep going. Finite means it stops, right? Infinite means it goes forever. This particular problem could continue going for a few more rows, but it would have to stop. Okay, now, hey. So now, it's the number of rows. Here I have one row. Here I have 1, 2, 3 rows. Here I have 1, 2, 3, 4, 5, 6 rows. You with me on that?
Yeah.
The number of rows. Let's just count. 1 row there. That's 1 row. Here we have 1, 2, 3 rows. Here you have 1, 2, 3, 4, 5, 6 rows. Here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows. Okay? So how do you go from 1 to 3? You could add 2, right? But does adding 2 work here?
Times 2.
Okay, so adding 2 does not work. That rules out this cannot be an arithmetic sequence. Does that make sense?
Yeah.
Because this is plus 2 and this is plus 3. It cannot be arithmetic. It cannot be arithmetic. So, is it geometric?
No.
Here I got to multiply by 3. Here I got to multiply by 2. That doesn't work either, right? So this is not geometric. So it's actually neither. Is it a finite sequence? Yes, it is. Let's do the next one. How many cubes are there? Well, there's 1 cube here. Here there's 1, 2, 3 rows by 1, 2 blocks. Right? 3 times 2 is 6. Here you have 3 blocks. And there's 1, 2, 3, 4, 5, 6. So 3 times 6 is 18 blocks. Here you have 4 blocks in a row. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So 4 times 10 is 20. Now, what do you do to go from 1 to 6?
Hold up, did you just hear yourself?
Did I say something?
It says 4 times 10 is 20.
Sorry, excuse me. 4 times 10 is 40. 4 times 10 is 40. All right, now, how do you go from 1 to 6? You could add 5, but does adding 5 each time work?
No.
So this is not arithmetic. Okay? What would you multiply by?
6.
You could multiply by 6. Does 6 times 6 equal 18?
No.
No, it does not. So this is not geometric either. It's neither, and this is a finite sequence. Okay, so.
Why do you say finite?
Because it's finite. It's infinite or it's finite. Okay.
How did,
Okay, so here's what I want you to do. You have homework. Your homework is to finish the rest of these slides. You have these patterns. Here you're dealing with the number of black triangles. Here you're dealing with the number of white triangles. Here you're dealing with the side length, the smallest shaded area within the unit square. So this is 1. So this is 1 by 1. That's a unit square, all right? So it wants the side length of the smallest shaded square. So it wants this, the side length, all right? So in this case, it's a half. And then the smallest here, a half of a half, that'd be a fourth, and then so on and so forth. So you can work on that problem also for homework. Your job is to finish these notes, and then we can check them. In fact, I'm going to go ahead and continue these notes right now so you can get online and do this yourself. But now here, we're looking at the number of shaded squares. Okay? And next one, this is a create your own sequence. And then it gets into the formulas. And these formulas were used actually by a few of you guys over here earlier today. We're going to talk about that. Those look fancy right now, but so finish this all up, guys, and have a great rest of the day. Thank you for watching.